All right, so this is lecture 20 in section 4. We are covering support vector machine basics, and this is the module 2 of the basic SVM. And in the first module of SVM, we covered history of SVM and also this the definition of large margin linear classifier. So in this module 2, we will define margin M in terms of the module parameters. Let's get started.
I want to do a handwritten derivation is because it seems pretty unintuitive about what is a region, so the margin in the different cases. So now let's do, so if my input is R1, so R1 means only one-dimensional real space, which means I have only one X. I'm trying to predict it into +1 and -1. And normal cases, if you think about what is this classification? So this is a one-dimensional value line, right? And I have some classes like on the left, I have some classes on the right, and this is one-dimensional classification, right? So I want to find the middle separating regions. And in fact, whatever point in the middle from the left, this blank region makes sense, right? And then I'm defining my classifier like this. The left boundary, right boundary, and the middle points. So every point on the left will be classified as -1 class. Every point will be as the +1 class. So, but in fact, on this number line, if this middle point is x0, I need to figure out who give me, so how do I represent x0? That's my question. How do I search for it in the one-dimensional case? How to represent decision boundary, actually it's a point in the one-dimensional case. Yeah, it's a little bit tricky, but actually in the end, I can just represent whatever it's our old equation, right? We're using a linear line to represent the separation, the middle of separation. So let's see this. So how to represent the region? We can use 3 lines. This line is the middle line, and then the 2 boundary lines. And the middle line is the line, it's a line, right? Just double transpose x plus b equal to 0, right? That's how we represent the line in RP space. In this case, actually there are 2x, and it's always representing as this formula if you want to represent a line. And let's make it more concrete. W transpose x plus b equal to 0. So that's the middle separation boundary. And our x is normally p times 1 vector, right? And then the w is our weight to learn. It's a 1 times p weight matrix. And the b here, it's a 1 times 1 scalar because the double transpose x plus b, and this is an inner product, this gives me a 1 times 1 value. And then the plus b, the W and the B is the one I'm looking for. This left side is -1, right side is +1, and it's a very natural thing. The middle is 0. And naturally, in the future, I can just use 0 to do the cutoff. So my fx function, right? My fx function is, my fx, whenever there's a future point, my fx function is W transpose x plus b. If it's larger than 0, I'm going to predict it as 1. If it's smaller than 0, I'm going to predict it as -1. That's exactly the decision boundary function, right? And then this is the, so fx equals to sign is my decision function. So the design of my decision function is there's a sign function. If W transpose X plus B larger than 0, I predict it as +1. If it's smaller than 0, I predict it as -1. The sign function is equivalent to, I'm using 0 as a cutoff, right? 0. If it's larger, go to the +1 class. If it's minor, go to the -1 class. And then the most important, the one in the middle, is the boundary I cannot decide. And that's the middle line of my whole region. So in the one-dimensional case, in fact, I just only need to know that 2 boundary position, right? This is called X left boundary. This is called X plus boundary. And I need to actually have 3 equations to solve. Because, like I said, it's a sign function. However, I want to represent everything in the middle. It's not very sure. Everything more than the right boundary is very sure. More than the left boundary, it's very sure too, right? So then I just design this. It's actually a design. The middle one is, assuming this is the x0, so X transpose x0 plus b equals to 0. That's just my design because that's my decision boundary. And then my left margin is, the left boundary is W transpose x minus plus b equals to -1. W transpose x plus 1 equals to b equals to +1. And this is my design of the region. And after this design, I guaranteed everything later will be predicted correctly. And then my decision function is naturally this function, fx equals to sign W transpose x plus b. When it's larger, it's very, very guaranteed. Larger than 1, it's very sure, and you're going to put it at 1. When it's smaller than -1, it's very, very guaranteed to be into the -1 class. Question about this. In the end, this is my design. It's a design, and I'm designing the region looks like this. And then what I need to look for is W and B. I'm searching a W and B to make this fit well in my training data. However, I actually do not know who is X minus, who is X plus, right? And I do not know X0 too. And then how do I formulate? What I really know is those on the right, those on the left. And how do I formulate it? My region formulation is boundary, but I need to know who are in the boundary, right? Who are the points on the boundary? So this just gives you a rough idea about the design of support vector machine. So this is the one-dimensional case. This is the two-dimensional case. And the p-dimensional case, the decision boundary has this formulation is the one with the 0, and the number itself tells you that's the point I cannot decide. I do not know it's -1 or +1 class. Question about this? Yeah. All right. So there may be some of you may question, why do I use this W transpose X plus B formulation? The reason is if a line in a two-dimensional space is represented from this formula, it's a generic formulation. If it's a line in a p-dimensional space, or called hyperplane in a p-dimensional space, it will have this formulation. And then we just reformulated actually by replace A1 onto AP into a vector W, and then this B, actually we just put on the left, and I can just write it like this, maybe make it more coherent, is this is a constant. Every hyperplane in a p-dimensional space, it follows this formulation. And we just reformulated by putting that constant on the right into the left. To make this as a formulation is W transpose X plus B equal to 0. But we need to search for who is the W, who is the B, using training data. Question? Okay. So now we already know we need to formulate the left margin, the right margin. But you might got confused with the regression. So in the regression, what we covered, well, we have a regression. We have y from R1, right? The output is only one y, and x is a vector from Rp. Maybe let's assume, for example, p equals to 1. And we normally write something very similar like this. So this is x, this is y. And if you look at this figure, we also have a line here. But this is x1, this is x2. And in fact, y is where? The y is represented as the symbolic, the x of the checker mark. More easier, let's look at one-dimensional case. So this is the two-dimensional, it's a line, right? So this is the regression, but it's also a line. And how do we normally write it? We write it W equals to y equals W transpose X plus maybe W0, and that's pseudo features. In fact, this follows the hyperplane formulation, which is W transpose X plus W0 minus equal to 0. The reason why I'm writing this is, in fact, this is a hyperplane in a two-dimensional space. It just, that two-dimensional space is x and y space. And this is what we mean a linear line, and it's actually a linear hyperplane in the x plus the y space. It's a p times 1 space in the regression case. In the classification case, in fact, let's see the classification, just the binary classification. You know, like our y is -1 and +1, right? If we have x from Rp, the same formulation, and p equals to 1 as previous page, what is the x1 representation? So I think in the previous page I had left. So what do my surface map look like? Actually, this is surface map. So what does this look like? The function I just defined. The function I just defined, when having both x and y, this point give me y0, right? This is wx. So that point is it's this x0 point, wx0 plus b equals to 0. That is my y. And then my left point, x minus, this is my x minus point. X minus is what? It's actually minus 1. I actually do not know the middle, but let's just assume it's. And then this x plus 1 point give me y of, oh, sorry, the pen seems to be not very working today. There actually should be a sign function there. So there's always a sign function. And then it's the prediction function actually looks like this. And this is the x-y relationship in the classification case. So this is the regression case. This is the classification case. In fact, I'm learning a stair type of function as the surface map. Question about this. But in the p-dimensional space, only in the xp dimensional space, it's actually a linear decision boundary, because the middle, those points satisfies this. It's a hyperplane, right? It's equal to 0. Every point on the decision boundary, and the decision boundary is a line or a hyperplane in the RP space, in the X space, because that's just the definition, right? It's definition. Those points on the decision boundary will follow Wx plus b equals to 0. All right, so I think this hopefully clear. In the two-dimensional, this is a little bit crowded. In fact, what I want to show, because I already have everything there, is only in the two-dimensional case. So when your feature is x1, x2, and what the y space, in fact, like what we learned, the y, so this is a linear decision boundary in the x1, 2 space. And the y, when you consider y, there's a stair come out, and it's the +1, and then on this region, there's a stair go inside -1. And that's what you learn. It's different, so you don't get confused with regression. All right, so question about this. This page is a little bit crowded. Yeah, I'm going to make it a little cleaner after the class. Yeah. All right, so like I said, it's design, right? I'm designing the boundary left is +1, the boundary minus -1, and the middle is 0. How do you look for it? How do you search to find the double and the B? And also those points on the boundary, actually you do not know who are on the boundary, right? It's a very complicated search task. And everything here, I mean, you're going to get larger than 1 because it's a linear function, right? And just using the sine function to push it to the +1. And this itself tells you how certain you are in the +1 region. And this tells you how certain you are on the -1 region. So now we actually specify this max margin classifier. If it's larger than 1, it's classified into 1. If smaller than -1, it's classified into -1. And actually in the middle, in fact, this whole formulation it's about, I'm not very sure. For those points who within the -1 and the +1, it's the fuzzy points. I'm not very certain. So this of course has this, you are assuming all the points can be separated completely by some region. But it's in a lot of real world data, there will be middle points. There's no way you can find the points are totally separated. So let's just do a simple case. We assume the data can be completely separated. And when you assume there's a completely separated case, and how do you search for W and B? So now, the most important, we come back. So I'm designing the max margin classifier like this. Boundary +1, middle 0, and then the other boundary is -1. But how do I know that's max margin, right? I mean, this whole thing starts with margin. I maximize the margin. How do this definition give me the margin formulation? How do I represent margin? And that's exactly is, after you have this formulation, the margin is easily represented by W. So the margin M, that's the width, is a very easy analytic form of related to the W vector. Let's just start to do a simple derivation, which is actually extremely simple. So I already did this, right? A number line, X on the left and right. So this is the X left margin and left support vector, the right support vector, and I want to learn the middle. X0 is the decision boundary line. And the margin is something called, it's really the wideness of that region. So what is M here? How do I know the wideness of M? Assuming I know X left, X right, and X0. What is M? What is the size of M? So very easy. M equals to X plus minus X minus. Okay? So, but I don't know what is X plus and X minus, right? But I know what? I know that three equations. I know Wx minus plus B equals to -1. Wx plus B equals to +1. Okay, now what should I do to get simplest equation cancellation, right? How do I do it? First equation minus, actually second equation minus the first equation. What do I get? Wx plus minus x minus equals 2. So margin equals to what? 2 over W. Actually, I need to guarantee, there's maybe this absolute values. If in the p-dimensional case, in the end, if you do a little bit derivation in the multi-dimensional case, in the RP space, m equals to 2 over W transpose W, taking, I think it needs to take the square root. Yeah, yes. The L2 norm of W. Okay, is this clear? In R1, it's in the p-dimensional case. This is the one-dimensional case. Very easy derivation. But if it's larger than 1, it's a little bit tricky, so that's why I only do the one-dimensional case. One-dimensional case is so intuitively easy. You just directly cancel the B, you get the W. Or you get M, yeah. All right, so now we know margin is 2 over the W vectors to norm. Because I want to maximize M, right? Then what it's equivalent to? To maximize the M, which means what? To minimize, it's equivalent to minimize W transpose W. So what is W transpose W? It's the L2 norm square of our weight vector, right? All right, so yeah, that's the same derivation, but I still want to do like step by step because you seem to get better if I do the derivation on the board. Okay, so now I want to, there are two goals at the same time. I want to classify all the training data correctly. That's my classification goal, right? The second goal is I want to find a region that maximizes the margin. And actually these two are all those related to the W and B. And I don't even need to search for X minus X class, those support vectors, and I can define the margin based on the W. Then the two goes at the same time. Maximize the margin, or equivalent to minimize L2 norm of the W vector. At the same time, classify all the training points correctly. So then how do you formulate this? So this is my objective. I'm minimizing W transpose W over 2. I'm subject to what? I want to classify all the points correctly. How do I know I classify all the training points correctly? This is the thing I can guarantee that. For all the X in the class plus 1, I want to get a W and B to give me values all larger or equivalent to 1. This guaranteed that positive class got predicted into positive. For all the points in the negative class, I want is this formulation W transpose X plus B to give me predictions all smaller than -1. And this guaranteed the second goal, classify correctly, and the upper part achieve the first goal to maximize the margin. Question about this formulation? All right. So, but in fact, how many constraints are here? Well, you have n total of number of samples, you have n different constraints to satisfy. At the same time, maximize the margin. So you can actually, you need to do a little bit from a reformulation is, so how do you combine these two different cases into one formulation? It's very easy. So when your 2y is positive class, and this gives you larger or equivalent to 1, right? You want to guarantee. And this will change to the different formulation as yi times w transpose xi plus b larger or equal to 1. And in the negative case, because yi equals to minus 1, and you require this part smaller or equal to minus 1, then the multiplication should be larger or equivalent to 1. And then this just coherent combine all this different formulation into one equation is yi w transpose xi plus b larger or equivalent to 1. And this is the final formulation. It's our loss function to optimize in SVM, maximize the summation of I from 1 to p wi squared, because that's the L2 square, and subject to all the I in the training data, yi times xi, x transpose, you should actually understand this formulation. Xi transpose W and W transpose Xi equivalent to each other, because that's in the product. And it's all larger or equal to 1. And this is called the linear separable support vector machine formulation. I think that's about it today. And actually, you can directly, using a quadratic programming solver, to solve this. The reason why I'm saying this is quadratic is your goal, because W is your parameter, right? And the objective function is Wi quadratic. It's a quadratic goal subject to, and this is a linear constraint. So yi is given, and this is a linear function, right? And when you have a linear constraint, quadratic objective to optimize, and this is a classic quadratic programming formulation. There are existing solvers to directly solve this. And quadratic object, I think that's it.